This lesson will be an introduction to limits going to infinity and limits as x goes to infinity. Section 2 of Chapter 2 in our calculus book. We are going to begin by studying a graph and table of the function y equals 2 plus 1 over x minus 3. I'll give you a chance to pause the video and enter that equation into your own calculator, into a graphing calculator, and see if you can answer the 5 questions listed there. Okay, by now you should have had time to enter this equation in your graphing calculator and explore it a little bit. I'm going to show you the graph on my graphing calculator, and we'll talk about what we see. So I put the function into y1. I'm going to take a look at the graph. Let's view this a little bit larger. And we see something unusual happening right around x equals 3. To the left of 3, I see the graph just falling off to negative infinity. If we were to enter some values, trace some numbers close to 3 but not quite there, for instance 2.9, we get a value of negative 8. 2.99, negative 98. 2.9999, negative 9,998. So the closer we get to 3, the lower these numbers get, down approaching negative infinity. Let's try a pretty large number, 2.99999999. And we're getting a very, very negative number there. If we come at x equals 3 from the right, let's watch and see what happens there. I'll try tracing with some values that are close to 3 but just above 3. For instance, 3.2. Well, there we've got a value of 7. 3.1 gets a little closer to 3, up to 12. 3.11, 01 is even closer to 3. 3.0001. And we see we're already at a value of 10,002, 3.000001. Well, our numbers are getting very large here. Now we're approaching infinity. 3.0000000001. So yeah, lots of numbers. An 11-digit number here. Although if I try to go to 3, I get no value at all. The function is undefined at 3, which we can see if we just examine the function. If I try to put a 3 into this fraction, I get 3 minus 3, that's 0 in the denominator. So I should expect to not get a value at x equals 3. But certainly something happens as we come at 3 from the left or from the right. So the next thing I want to explore is what happens to this graph for very large values of x. So we're centered right around 3 here, but what if we go far, far off to the right? Let's change my window here. Let's say our window is maybe negative 10 up to 10,000. Let's take a look at that graph. So we can just barely see anything to the left, but we do see that this function seems to just continue off there in a straight line. So I wonder if that really is a straight line. Let's trace again. And I notice that for some values I get fractions, other values the calculator can't even turn it into a fraction. But for very large values of x, we seem to be hovering right around a value of 2. Even these fractions I see, the top is just a little more than twice as much as the bottom. And notice this, somewhere in the 5,000s, we've gone from 2.0002 down to 2.0001. So somewhere around 5,060, maybe 50/50. I don't know, let's try a few numbers here. 50/50. Oh, it tells us a fraction. 50/51. Fraction again. 50/52. 50/53. Well, if we go far enough here, we start getting decimal values. But somewhere around the 5,070, maybe 5,050, 5,060, we're going to get a decimal value that is less than 2.0002. Now, once we get that far, we're going to notice that the decimal values stay below that. And in fact, they continue to decrease, but they never go below 2. I wonder, will it ever actually reach 2? So that's the last question to consider. Will this ever reach 2? Well, the answer is no, because if I put a value in for x and subtract 3 from it, I'm going to get a fraction. It may be a very, very small fraction. So if I put in 103 for x, I get 1 over 100. If I put in 1,000,003, I get 1 over 1,000,000. But it's still something that I'm adding to 2. And 2 plus something is always more than 2. There's no way that we can get an x value which would make this fraction equal 0. So there's no way I'm ever going to be adding 2 plus 0. Just cannot happen. So we'll never exactly reach 2. What we've really been exploring here are two ideas. We've been looking at the idea of a simple limit, like limit as x approaches 3 of a function, and approaching from the left, we saw that this function went down to negative infinity. The limit was not a number, but saying that the limit is negative infinity means that the function just continues down forever the closer we get to 3. From the left. From the right, we looked at limit as x goes to 3 from the right and saw that the function increases forever, increases without bound. And we'd write that by saying that the limit equals infinity. Now, the other concept we looked at was the idea of letting x go to infinity. So letting x be very large numbers and continue forever to the right on the number line. What was this limit? Well, graphically, we can sort of intuitively understand it seemed to be getting closer and closer and closer to 2, so maybe the limit is 2. We didn't look at this on the graph, but we'll also consider limits as x goes to negative infinity. Those would be considering what does this function do as x gets very, very far to the left on the number line. So with large negative numbers, negative 1 million, negative 1 trillion, negative 1 trillion trillion billion. What does that function do? Does it seem to get close to a number, or does it do something else? At this point, I want to give you an informal definition of limit as x approaches positive or negative infinity. So this is not a formal definition. It's not a mathematical definition. It's not going to involve fancy mathematical notation too much, but should give us an intuitive idea of what we're thinking of when we do one of these kinds of limits. So our first condition is if x is far enough to the right or left, then our function f of x gets close to some value L. In our example, as x went very far to the right, f of x got close to the value 2. Our second condition, we can make f of x as close to L as we want by making x far enough to the right, or in the case of negative infinity, going far enough to the left. But f of x does not have to ever equal L. We saw this in the example that we could get very close to 2. We could get closer than 2.0002 just by making x big enough. X got up past 5,050 or 5,070, and at that point, the function was close to 2 within 0.0002. If we had wanted to go within 0.000002, we would have just had to move x far enough to the right. Maybe that would have happened at 10,000 or somewhere out there. But for somewhere far enough, f of x got close to L. Here's another condition. Once we go far enough to the right or left, f of x never goes farther away from L again. So what we noticed in that function was once I was within 0.0002 of 2, as I continued to the right, the function never got farther away from 2 again. The function didn't turn back up and suddenly jump out to a value of 3 or 4 or a value of 2.5. It always stayed that close to 2 and got even closer to 2 after that. If all these things are true, we say the limit as x goes to infinity of f of x equals L, or the limit as x goes to negative infinity of f of x equals L. So the way I like to think of this informal definition and the way we can think of limits going to as x goes to infinity is like this. Suppose that number L is maybe right here. This is the y value that we think the function is getting close to. I'm going to draw a dotted line at L. So what I can imagine for a limit as x goes to infinity is, imagine that we've got a car here. And the function value is the height of the car. And what happens is the car approaches a tunnel. And that tunnel is kind of an unusual tunnel because the farther that tunnel goes to the right, the smaller the tunnel gets. But since the height of the car is a function, the height can change. This car can shrink. And if our function shrinks so that it can stay within this tunnel, then we have a limit that's approaching L. Now, somewhere out here, this tunnel is going to get smaller. If I want the tunnel to be only 10 feet tall, at some point, the car has to be able to shrink far enough to fit in a 10-foot tall tunnel and then stay that small or smaller forever. At some point, that tunnel is only going to be 1 foot tall. Can the car shrink down to fit under a 1-foot tunnel? I can make that tunnel arbitrarily small. So I should be able to make that tunnel a centimeter tall or a millimeter tall. And the car has to be able to continue to shrink to fit inside that tunnel, getting closer and closer to L. If that is true, if it can stay inside that tunnel and it never at some point enlarges again and breaks its way out of the tunnel, if it always stays within that constantly shrinking tunnel, then we say that we have a limit as x goes to infinity. The function gets closer and closer to L the farther out we go to the right. And if we want to get close enough to L, we just have to go far enough out to the right. I should be able to get as close as you want me to get. You can make your tunnel as small as you want, and I should still be able to fit the function inside that tunnel, approaching that value of L. That's going to do it for this introduction to limits as x goes to infinity or limits that go to infinity. We'll continue chapter 2 at another time. Thank you.